right, good afternoon, everyone. It's nice to see you all here and to not see some of you here, but imagine that you're out there in the ether, hopefully enjoying this as well. I think it's really exciting to be able to have a visitor in person, so I'm happy to introduce to you Professor Jonathan Simon, who was nice enough to take the red eye last night so that he could be with us today, visit a bunch of labs, ask great questions. I have to hold the mic higher, I'm not used to these mics. Professor Simon is someone working at the interface of quantum optics, cold atoms, quantum materials, topological materials. He did his PhD at Harvard and MIT with Laughlin, also working with Misha Laughin, going on to work with Marcus Greiner, doing a lot of really exciting pioneering work on quantum simulations, cavity QED, et cetera. But then spent 10 years as professor at the University of Chicago with his teammate, David Schuster, really pioneering all sorts of exciting work, studying materials made out of light, the kind of stuff that he'll be telling us about today, and has just recently moved to Stanford University, where he's going to be continuing this venture. So I won't take up more of his time, but I'll just ask you to join me in welcoming Professor John Simon.
All right. Well, I have to say it is really a pleasure to be here. I want to warn you at the get-go, this is my first in-person colloquium in 2 years. So if I'm a little rusty, feel free to give me feedback, but be gentle. Faculty have feelings too. I know many people don't believe that, but I think there was a study in the mid-80s that showed that to be the case. Not many, but some feelings. Anyway, I have to say I've really enjoyed all the lab tours I've had today. I'm looking forward to, I guess, a couple more later in the day. So I really appreciate everybody's time and engagement. It's been a pleasure. What I'm going to tell you about today is ongoing work in my group and in collaboration with Dave Schuster's group, making matter out of light. And there's this quantum in there, and we'll talk about what that means as well. But I think a good starting point is to just ask this question. When I say we're going to make matter out of light, you know, what do those words even mean to me? What should they mean to you in this context? And to some extent, this is really what's fun about this story, right? We're developing these tools, we're studying quantum mechanics, we're going to study some many body physics, but I hope that this will inform you a little bit about what these rules of condensed. Is this too loud or is this good? It's good. Okay. You sure it's okay? Because like I'm hearing a lot of myself. Like, you know, most faculty love to hear themselves talk, but this is really a lot. Anyway, so, you know, I think it really does speak a little bit to these ideas. What does it mean for something to be a material? So let's jump in. To me, and in the context of today's talk, a material is a collection of particles that interact with one another and can thereby sort of organize their order. So what I've got for you here is a little simulation that I wrote, totally classical. Each of these little balls has some mass. Each ball is attracted to each of the other balls when they're far apart. And as they get close together, they start to repel each other. And then I add a little bit of friction. So what happens when we start this dynamics evolving? Well, we immediately get a classical crystal out of this. Did I tell the thing that it should make a hexagonal lattice, triangular lattice, depending on how you want to think about it? No, I didn't have to. All I had to do was put in those fundamental ingredients of particles that interact and a little bit of friction to take out the excess energy, and I get this crystal with phonons and so forth. Sort of, it emerges for free from the underlying rules. So if we want to study this kind of physics with light, the things that we need are a collection of particles. So what does that mean? I would say a particle is an object that responds to forces applied to it in some kind of a sane way. Okay, we need interactions between the particles. That is to say, when the particles are far apart, they attract. When they're close, they repel, or something like that. And then I need some way to help the system order. I need some way to suck the entropy out of the system, et cetera. So, and then there's this separate question, what makes the material quantum? And I'm going to make a statement here for fun. I'm sure people will have lots of opinions on this, and that's good. I would say a material is quantum if entanglement between the particles controls the material properties. So what that means is the dynamics of the particles and the collisions between them should be faster than the coupling to the outside world, which sort of destroys the coherence that came from the collisions. Okay, now for context, this means a bunch of marbles form a material. They satisfy these requirements, but it's not a quantum material, right? Because they're constantly colliding with air molecules that's destroying any entanglement between them. By contrast, a hydrogen atom would be a quantum material, right? The interactions between the electrons and the protons determines, say, the optical properties of that atom, right? And you need quantum mechanics to understand that. You need quantum entanglement between the particles to understand that. Okay, so if we want to make a material out of photons, the photons need to act like particles in some kind of a sane way. So if I have an electron that's moving to the right and I apply a force to the left, it will slow down and then move back to the left. If I have a photon that's moving to the left and I apply a force to the right, it changes color. So that's what, when I make this comment, it has to be sane, right? This is not a sane response to a force. So why does that happen? Well, basically, a force changes the momentum of the photon, but the sort of effective speed of the photon is determined by the slope of the energy momentum relationship, and that's linear for a photon in free space, right? And so as a consequence, these photons don't respond to forces in a sane way. They don't have an effective mass, if you will. By contrast, if you trap your photons in some kind of a metamaterial, you can change the dispersion relation of the light, and I'll give you some concrete examples of that. And that's going to allow us to create photons that act like sane massive particles in response to forces. Okay, so that was challenge number one, and that's broadly how we're going to deal with it. Challenge number two is if I have two electrons, when they get close to each other, they can collide and bounce off and fly apart. What do we know about light? Well, if we know that if this is a solution of Maxwell's equations, and that's a solution of Maxwell's equations, the sum of the two is also a solution. The photons just go right through each other. Put another way, we don't live in the Star Wars universe. These photons don't collide, right? Well, if your photons don't collide with each other, right, then they kind of can't order. And so that's not good for material science. So we need some way to make these photons collide, and we're going to take some inspiration from electrons. So how do electrons collide? Well, through the Coulomb interaction, which is the exchange of virtual photons. Okay, so you might say, maybe we could have photons collide through the exchange of virtual electrons. Well, that Feynman diagram is disallowed by all of the symmetries. But you can draw a more terrible one that is allowed, but it's very small. But the idea is right. The way our photons interact with each other is by interacting with matter. The material particles will interact with each other and then back act on the photons. And that's basically how electrons interact with each other, but in reverse. Okay, so we're going to need to have some material in here that mediates the interactions between our photons. Okay? What's the third challenge? Remember I told you if we want to study a quantum material, we want the collisions between the particles to be very fast compared to any damping timescale, right? Because damping entangles you with the outside world and destroys any quantum coherence. So what happens to this model if I run it without any damping? So you could call that just a bunch of angry bees. You could call it, graduate students at cookie hour. you know, whatever your favorite analogy is. But this is to say that if you don't have any damping, it's not clear how to get your system to the many-body ground state. It may be evolving, it may be developing entanglement, but if you want to study the low energy properties of the system, you want to study the kind of materials that you might get out, you need some way to get the system towards its ground state. Okay, and so we have ideas for building the material up particle by particle in the ground state, or ways of sort of implementing local cooling. So time permitting, in the next 2.5 hours, I'm going to tell you 2 different stories. I just like to say that and see if anybody tears up a little bit. Let's make sure you're all awake. I've had a lot of coffee today. Ephraim's asked me on 3 or 4 occasions, would you like some more coffee? I don't even know why he's asking. Every time the answer is yes. But I'm going to try to tell you about 2 different sets of experiments that we've done. One with microwave photons, where we trap them in lattices of resonators to kind of make them behave like massive particles. And then we use the tools of circuit QED to make them interact. And the other platform will be optical photons, where we trap them in optical cavities and have them interact with Rydberg atoms to make them collide with each other. And my hope in going through this, as well as seeing some, what I think at least is very cool physics, is that you get some flavor of what it means to manipulate the dispersion of particles, to control the behavior of the individual photons, to make them behave as particles in some kind of a physical sense. You get a flavor of what it means to engineer a physical system where the photons collide and what ingredients you might want there. And also a taste of what some of the challenges are for building up many-body states. And if you have absorbed all of these things, you've finished your PhD in my group. So good work. But this is, you know, at some level, what I hope that you can try to get out of this. And I'm going to tell you 2 separate stories. So if you do lose the thread at some point, at the end of the intermission for each of these stories, you can feel free to you know, wake up a little bit and maybe try again for the next one. But hopefully you will all be so smitten with excitement that that won't be an issue. Okay, so before we hop forward, this is the first of the 2 intermissions. Do people have questions about these broad ideas? Don't be shy. That's my cat. Her name's Emmy. What I'd like to do is start by telling you a little bit about making materials out of microwave photons. I think in some ways this story is a little bit easier to digest. Okay, so what do we know? Electronic materials come about when electrons hop around in some ionic lattice, right? And so the 2 sort of fundamental ingredients here, I'm pretending electrons are bosons, which isn't quite right, but you know, I do quantum optics, so everything's a boson. The 2 terms here are this first one, which is a hopping term, where particles can hop between site J and site J+1. So that kind of looks like this. This color was much brighter on my laptop screen. And the second term says that you pay an energy cost to have 2 particles on the same site. Okay, and this is how, in a lattice model, I would like you to think of a collision. The particles have trouble hopping on top of each other because there's an energy cost associated with that, which is potentially, no pun intended, larger than the kinetic energy. I swear that was not intentional, but I'm going to use it every time from now on. Okay, but the point is, these are the 2 ingredients that we need. We need like little wells that our photons can live in and hop between, okay? And then we need some way to pay an energy cost to have 2 of them in the same well. Doesn't sound so hard, right? Well, it turns out that, that it is very hard. And the tools have kind of been developed over the last 20 years to build these things up. And I'd like to give you a sense of how that goes. So there were a ton of ideas of how one might go about this. And all kinds of pictures of what such a system would end up looking like. Our idea, and what I'm going to tell you about today, has the most in common with this proposal from Andrew Houck's group. This is a collaboration with Dave Schuster. You may recognize this as the Simon & Schuster Publishing House logo. Our hope is that at some point we get famous enough that someone cares enough to sue us. But I think we're pretty far from that point. Okay, so what are the things that we need to do? We need to figure out how to make a latticite that can hold these photons. Okay, so what is a latticite that can hold photons? I would claim an LC circuit is a latticite for photons, right? The frequency of those photons is 1 over root LC, right? That's the resonant frequency of the circuit. It can hold, oops. I don't know what just happened, but it wasn't good. There. It can hold 0 photons, or if you put a photon in, that costs you an energy of like Planck's constant over 2 pi root LC for the first photon, which here I've set to 4.5 gigahertz. And if you put another photon in, it costs you another 4.5 gigahertz. And if you put a third, it costs you another 4.5 gigahertz. So this is great, except remember, one of the ingredients that we wanted was you have to pay more to put in the second photon, right? That's what collisions between our particles would mean. So how do we get that? Well, one thing that you do know is if I run enough current through this inductor, it'll start to deform, right? It melts, right? So what that means is its shape probably changes. So its inductance would change, right? And so eventually this resonance frequency changes, but it's up at like 10 to the 15 photons, right? That's too many. We want it to happen at 2 photons. So the first thing you might do is say, well, let's make this inductor really, really small so it takes less current to heat it up, okay? And in some sense, that's the right idea. You have to go a little bit further than that. What you really do is replace this inductor with the smallest thing that behaves like an inductor, which is called a Josephson junction, which is sort of Cooper pairs tunneling back and forth across a barrier, ends up behaving like a very nonlinear inductor, okay? Meaning the inductance depends extremely strongly on the current, such that the first photon that goes in needs to have 4.5 gigahertz times Planck's constant of energy, and the next one needs to be at 4.2 gigahertz, or thereabouts, okay? And to be clear, if you who's read about these quantum computers at Google and IBM and Amazon and these places? This object is what they call a transmon qubit, okay? Now you're like, but you just threw 3 levels. In what sense is that a qubit? A bit has 2 levels. Well, the essential point is because it's nonlinear, if I drive this transition, I don't also drive that transition, right? And so you can use it as a quantum bit, okay? And our realization here is that you can also use it as a site in a lattice, right? Where if you put 2 photons into that site, they're attracted to each other by about 300 megahertz. Okay? We on the same page? So what happens if I want a photon to hop from this lattice site to that lattice site? How would I make that happen? Couple them with a capacitor, right? And the bigger that capacitor is, the more tunneling I have between the lattice sites, okay? And the thing that's amazing about this approach is that you literally pattern aluminum onto a sapphire substrate. It's literally a circuit, right? And it has sort of the quantum coherence properties equivalent to cold atoms in an optical lattice. Yes? So you're asking why is it lower as opposed to higher? It's lower in this case because the kinetic energy in that gives rise to the Josephson effect goes like the cosine of the phase. So the potential is gets softer as opposed to stiffer. There are ways around that. So you're asking why, is it a problem that it's attractive? So what we'll see is that for the experiments that we're doing, everything's just flipped, so it doesn't matter, okay? But fundamentally, there are qubit architectures. If you look up like a biased fluxonium, then you can get, but this one behaves the most in the sort of simplest way, like atoms in an optical lattice, so that's what we've gone with. So the figure of merit, though, is how many collisions we get between our particles before they decay. Okay, so you say, wow, the photons only live for 40 microseconds. That doesn't sound like very long. Well, they collide 300 million times per second, right? So we have, 12,000 collisions within their lifetimes, which is more than enough to build up some ordering of these particles. Okay, and to be clear, this is on the order of what you get with cold atoms. There, maybe your interactions in a lattice site are 300 hertz to a kilohertz. And your lifetime is, 10 seconds, a minute, something like that. So it's perhaps surprising, perhaps not, that, if you look at the scale invariant, or the unitless quantities, the performance is similar. Okay, so what we're going to do is we're going to build a lattice of these things, and I'll show you a picture of it in a second. It's just a bunch of these transmon qubits capacitively coupled to each other. Okay, and then we're going to have the on-site energy be much larger than the tunneling. And the first question I want to ask is, what is the ground state of that system? Well, you're seeing it right now. There are no photons in there, right? And this is also true for cold atoms in an optical lattice, right? We talk about the ground state, but really you mean the ground state at fixed particle number in the system, right? And the problem here is we would like to prepare the ground state. How do we prepare this ground state at some finite particle number? So you could think about just shoving particles into the system with some coherent drive, but it turns out that won't prepare the ground state. And so what we need to do is come up with some object to couple to the system such that we get the ground state and not the grad students around cookie hour kind of picture. Okay, so what's the object that we want to build here? I would call it kind of a chemical potential. This magic object that I've drawn here, if it is ever empty, it refills itself with one photon. Okay, and then I couple that to this system. So the idea is that first photon can now hop into my lattice. Okay, and then this thing refills itself. Now, can the photon hop into the lattice? No, right? Because it has the right energy to hop in here, but it doesn't have enough energy to be the second photon in the lattice site. Or, as you pointed out, it has too much energy, but it's sort of the same. But eventually, this photon will randomly hop over by one site, and then this one can hop in. And then this refills. And so forth, and this will fill up your whole system. So you can see there's this is effectively making continuous measurements of the system, but only at this end. So it's not preventing quantum dynamics from occurring over here, just at the connection point. And we've kind of shown, in fact, that this kind of an approach works anytime the state that you're trying to make over here is incompressible, right? That is to say, here it looks like sort of a trivial state, one particle per site, like a full egg carton. But if you had some non-local interaction, if you were in a Landau level, et cetera, where the ground state has strong entanglement between the particles, but it also at some point costs a bunch of energy to add another one. As here, it was no energy cost to add them until it's full. And now to put another one in, you'd need more energy, right? Any system that has that property, you can fill in this kind of a way.
You said you like interruptions. What you've prepared here, as far as I can see, isn't the ground state. You don't have any dissipation. The ground state, you put all the photons in the same site since there's an attractive interaction, right?
You're saying this is not the ground state, it's the highest energy state. Is that what you're saying?
Yeah.
Yes. But there's sort of a symmetry, as it turns out, between, at least within a fixed particle number manifold, between ground state and highest energy excited state. And I think that's sort of another interesting aspect of this story. But okay, so this is the idea, and then we need to figure out how to make that object. So everything but this is easy to understand from this picture. The idea is that each of these little crosses that I've drawn there, I mean, this is actually a colored micrograph of the physical circuit. Each one of these is one of these qubits, okay? They're close to each other, which provides the capacitive coupling, the photons, the ability to hop from one to the next, okay? And then we can read out through these little microwave resonators the occupancy of each of the cavities with single photon resolution, okay? So for those of you who have heard of like a quantum gas microscope, this is sort of the equivalent. This is a quantum gas microscope for microwave photons. The only thing we're missing is how to build this object that constantly refills itself with a single particle. And so what we would like, to be clear, is some circuit element that, if it ever has 0 photons, refills itself to 1 photon. So you might say, let's just put a coherent drive between 0 and 1. Does that work? Well, what do we know? If you're in the 0 state, that coherent drive will take you up to the 1 state. Sounds good so far, right? What if you're in the 1 state? It Rabi oscillates you back down to the 0 state. If you're in 0, it puts a photon in. If you're 1, it takes a photon out. That is not what we wanted, is it? We wanted something that if you're in 0, takes you to 1. If you're in 1, it leaves you alone. So for anyone who has ever made a laser from scratch, who's made a gas laser? Only person in the room. Have you made one, Ephraim? Me neither. We've got one seriously old school nice guy. So the basic idea is you would like to generate an inversion here. If you forget that these are states of a qubit, you're just saying, I would like to, if you will, optically pump this system into the state with 1 photon. So how do we do that? We find some way to excite it from 0 to 2 and make 2 decay fast to 1. Okay, so how do we do that? Well, this is at a different energy from that. 2 to 1 is at a different energy from 1 to 0. So all we need to do is damp this guy with an RLC circuit resonant with the 2 to 1 transition. So it's quite neat. We're dealing with very quantum devices here, but you can still just build a little RLC circuit and couple there to make this 2 photon state decay fast. Okay? And then we just use a 2 photon drive to excite from 0 photons to 2 photons. And that makes this thing go. So anyway, this is just to show that we can do microscopy of this lattice. We can check whether it has 0 photons or 1 photon. If we have 2 wells, we can watch the photon Rabi oscillate back and forth between them. If we have 4 sites, we can watch a quantum random walk amongst them. And indeed, if we take a 7-site lattice and couple it to this stabilizer, what I'm going to show you here is the occupation of each of these 7 sites as a function of time after we turn on this stabilizing device. And indeed, what you see is the system goes from empty to full over a couple of microseconds, and then just remains full thereafter. Okay? And so that says that, you know, we've kind of made this crystalline state a so-called Mott insulator of photons. And you can then even ask the question, what happens when, due to the finite lifetime of the photons in this lattice, we lose one? Well, what we can do is prepare the state, remove the photon from the end site, and then if the stabilizing drive isn't on, that hole random walks back and forth in the system. If the stabilizing drive is on, the hole random walks until it gets to this stabilizer, and then it just gets refilled. Okay. So I would say in some ways I've shown you how to make a what we would call a Mott insulator or a crystal of photons. What if we want to make a fluid of microwave photons? So the problem with a fluid is that they typically tend to be compressible. And so this kind of dissipative stabilization is going to be hard. But what I'd like to show you is that there's actually a really cool approach that you can use with addressing individual eigenstates of the system through disorder. Okay? So we're going to try to make a fluid the ground state where the number of particles in the system is less than the number of lattice sites in the system. So let's suppose that what I really would like to do is prepare the ground state with one particle in the system. So who studied a particle in a box? Yeah? So the ground state of like a continuum system is going to be some sinusoid, right? So how do I prepare one photon delocalized over a whole lattice? Well, what you can do is start by having a whole bunch of disorder in your lattice. Okay? With all that disorder, what's the lowest energy state? Well, clearly just a photon localized in that site. Right? That site's the lowest energy, so the red shows we just put a photon there. What happens is I adiabatically reduce the disorder. Well, my claim is that when you adiabatically reduce the disorder, you should go to the single particle ground state, which is one photon delocalized over the lattice. Okay? And so indeed, we can actually do that numerically, and we can also do it experimentally. And so we can see that we can generate the lowest energy state, the first excited state, the second excited state, the third excited state for one particle in this lattice. But this then suggests something quite cool, which is if I have 3 particles in the lattice, and this is what the lattice looks like, well, we know what the lowest energy state is. Again, if there's disorder, right? One particle in each of those 3 lowest energy states. And then when I ramp that to degeneracy, it should make some strongly correlated entangled fluid of photons. Okay, and so we actually do that. And you see this object, which I would call a 3-photon strongly interacting superfluid. And I think we'll skip this melting piece of the story. But I think it's worth saying that you can then look at the correlations between the photons for either 2 or 3 photons. And you can see that even though the interactions are only on site, if you detect one photon at a particular site, it's, sorry, a little feedback there. It's quite unlikely that the other photons will be on even adjacent sites, indicating that we've kind of made this ground state of the system. And indeed, there are also some single site tomography reversibility type arguments that you can make there. So I think that's a good place to leave this piece of the story. I'll just say we've recently been building what looks like a sort of analog of a Josephson junction in this system. And we can see Josephson oscillations in this lattice of Josephson junctions, which is kind of fun. And so where this will probably go next is starting to push towards making some topological states of these microwave photons. Okay, so I think we have a little bit of time left, but are there questions on that piece of the story before we talk about optical photons? Okay. Yes.
Are these systems? Yeah, sorry. How big are these systems like that you engineer? Are they like 7 sites, you said?
Yeah, so you mean physically, how large are they?
Yeah, yeah.
So each of the transmon qubits is like a micron or two.
Oh, sorry. I meant like, how many of these qubits do you have arranged in a system?
Ah, that's a great question.
In a circuit.
So in the one that I showed you, it's really 7 or 8 qubits.
Right.
Okay. And I would say in some ways, this is the big weakness of the circuit platforms. People can do 80 or 100 sites. You know, Google's even a little higher than that. But the basic challenge is the qubits are not all identical. So you have to work hard to characterize them and make them identical. It can be challenging to avoid crosstalk during control and readout because these are RF signals and the objects are close together compared to a wavelength. So crosstalk is an issue. And the last challenge is a control challenge. You need to have RF drive lines running to each qubit in most architectures. And so that means you need, for 150 qubits, you need 150 5 gigahertz RF lines, right? Now, there are ways to get around that with frequency division multiplexing, right? But I would say the fundamental challenges are ones of control and dealing with non-identicalness of the system. So our plan is to kind of go up to, an 8x8 kind of system soon, but in some sense, I would say that's the limitation of these platforms.
Yeah, I guess I asked because it seems that you can engineer 2 different phases, which are these, the weakly interacting superfluid and this strongly interacting superfluid. And I was wondering if you can study the transition between the two, but normally for a phase transition, you need some kind of large averaging, over a large system.
I think this is a really good point, and I do have an opinion on this, which may not be everybody's opinion, but my opinion is that for the most part, the interesting many-body physics that ends up mattering in macroscopic systems has to come about from entanglement of not too many particles, right? Because if you were getting a ton of particles very highly entangled, it would be extremely susceptible to all kinds of decoherence mechanisms, right? And so my hope philosophically has been that if you can get to something like 8x8, so that your system has a real clean bulk and edge effects aren't too terrible, or just do periodic boundary conditions, that for the most part, the stuff that we're interested in should already be there. Now, to be clear, there are all of these questions in many-body localization, eigenstate thermalization, these sorts of things where you really do want a bigger system. And it's not that those aren't interesting questions, but I think if you want things that maybe connect more to the real world, to the extent that any of this connects to the real world, it should sort of appear in a fairly small system.
Okay, thank you.
Okay, so I'll spend the last couple minutes telling you a little bit about optical photons. And I think the main thing to take away here is how we engineer these kind of ingredients for the optical photons, rather than getting too much into really building the topological matter. Okay, so the first thing that I would like to convince you of, and I think this is sort of the most important part, is that photons in a multimode optical resonator behave like massive harmonically trapped particles. Okay, so what do I mean by that? So I've got 2 mirrors here, and I'm going to shine light into the cavity, and I'm going to look at what happens to that wave packet. And my claim is that it will oscillate back and forth transversely as though it was a massive harmonically trapped particle. So let's see if we can understand what that analogy kind of means. If you just watch the ray trajectory through this cavity, what you can see is that it does oscillate back and forth, right? Why does it turn around? The curvature of the mirror kind of refocuses the rays, okay? And if you only look in this central plane of the cavity, what you see is the wave packet kind of stroboscopically crossing there, back and forth, okay? And in fact, there's a whole flow K theory that we built around this. I don't think we need to go through that too much. I think the important thing to say is that the curvature of the mirror provides effectively the harmonic trap, okay? And the fact that the photons are moving mostly this direction at the speed of light, we never slow the photons down, right? They always move at the speed of light. But as I apply a force to them in the transverse direction, it changes the tilt, right? And so they are responding to transverse forces like massive particles. They don't respond to forces in this direction like massive particles, but in these transverse directions, they respond like massive particles. So you might say, is this hand wavy, or is there some sense in which this analogy is really pretty good? Okay, so the eigenstates of a quantum harmonic oscillator, as you may be aware, are Hermite-Gauss in space, right? And they're uniformly spaced in energy. So we've got one gas laser person here. Has anyone else looked at the spatial modes of a Fabry-Perot resonator? Did you find them to be Hermite-Gauss in space and uniformly spaced in energy? No? Okay, there's something wrong with your resonator. Take me down to lab later. We find, I don't know what kind of mirrors you've got in there. If you do it with spherical mirrors, you get that the transverse spatial modes are Hermite-Gauss in space and uniformly spaced in energy. So that is to say, if I send light into the cavity off axis, I can write that as a superposition of the lowest transverse mode and say the first transverse mode, right? Because those will destructively interfere on the left and constructively interfere on the right. But because they have different energies, half a cycle of this energy difference later, that plus sign becomes a minus sign, and now my photon has moved over to the other side, okay? And that's equivalent to this ray picture that I drew for you before, okay? And so that is to say that this story is not just kind of a qualitative hand-wavy story. There's a sense in which the photons really obey the same wave equation as massive harmonically trapped particles, okay? And so you should think of your photons as kind of living everywhere longitudinally and oscillating back and forth like massive particles in a harmonic trap, okay? So then we asked, is there a way to have these photons experience a Lorentz force? Because one of the things that we would like to do is explore the fractional quantum Hall effect for photons. The fractional quantum Hall effect occurs when you have electrons confined to 2D, so in magnetic fields in the third direction, right? So these electrons undergo little cyclotron orbits and then can collide with each other. So we're going to need to figure out how to make the photons collide, and we need to figure out how to make them behave as though they're in a magnetic field, experience a Lorentz force. Okay, so who has ever seen a World War II submarine movie? Okay, you know how the submarine captain looks through the periscope? And did you ever wonder why they have to turn the whole periscope around? Why isn't there just a crank that turns the top mirror on the periscope? Well, I'm going to tell you, and it's the way you make magnetic fields for light. If you look at this tree through that periscope, everything's great. But what if I rotate the top mirror by 45 degrees with respect, or 90 degrees with respect to the bottom mirror? Then the tree comes out rotated, okay? And so as I rotate the top mirror with respect to the bottom mirror, the tree orientation changes. So if you've ever built a beam elevator in your lab, we worry about this mostly for the polarization of the light and due to birefringence of the mirrors and other stuff. But fundamentally, if your beam wasn't circular, you would also see it get rotated by this, okay? And so what we do is we make a cavity like this, and then we add 2 more mirrors to close it into a loop, okay? So on each round trip, so we fix it at some angle, some rotated angle like this. And then on each round trip through the cavity, in addition to experiencing that harmonic trap, its trajectory also gets rotated a little bit. Okay? And that turns the lab frame into a rotating frame. Well, what do rotating frames do to particles? They make them experience Coriolis and centrifugal forces. So your Coriolis force looks like omega cross P, and your centrifugal force is an outward going force, in this case, a real force, because the lab frame is the rotating frame, okay? A real force that increases radially with distance. So we just compensate this one with the mirror curvature, right? Because remember, the mirror curvature gives us confinement, and this gives us anti-confinement. And the point is, these two terms look the same. So Coriolis force is a Lorentz force on the photons, which is to say, if you played tennis on a rotating tennis court, once you got over the nausea, your photon would experience a centrifugal force from your perspective, but it would also experience a Lorentz force. So if you wanted it to not experience the centrifugal force, what you would need to do is put a Dirac string, a bunch of charges along the central axis and have your tennis ball be charged, okay, to give you that repulsion or attraction to cancel out. So if anyone wants to collaborate, I'm looking for someone to make that tennis court, not really. So anyway, the point is, this is quite neat because now you just make this cavity, and when the twist creates a centrifugal force which cancels the harmonic confinement of the due to the mirrors, you're left with Landau-Levels for light. And so indeed, we can just build these cavities. It's just 4 super mirrors stuffed into a crazy 3D printed structure to get the angles right. And when we tune things properly, these modes form Landau-Levels that become degenerate to a couple of megahertz. There's a whole story there. The last piece that I'll tell you is about how you make these photons collide with each other. Okay? And this is a story of Rydberg EIT. So what I would like you to consider, I've got a cloud of atoms here, all sitting in this ground state. And I'm going to send a photon through it. Okay? The idea is, when that photon enters this cloud, it excites some atom up to this 5p state. Okay? Because the photons are resonant with the atomic transition. And then we just have another very strong laser that takes any atom that goes to the 5p state and excites it up to this high-lying Rydberg state. Okay? This Rydberg state is very long-lived. We use like 110 or 112. So it can have, millisecond kind of lifetimes. But the point is that now the photon effectively slows down. Why does it slow down? Because mostly it's not a photon. Mostly it's a Rydberg excitation of this cloud. So if you just had one photon, it would go in, slow down, and eventually be re-emitted as a photon and just go straight through. So far, so good? What happens if a second photon enters the cloud? Well, if it's near this first photon, it will try to excite a second atom up to that Rydberg state. But the problem is, by the time you get up to n equals 110, the electronic orbitals are like a micron or 2 in diameter. Okay, and so what this means is, for the second photon, that Rydberg state has moved away by many megahertz. So that second photon moves through the cloud very fast, but only if it's near the first photon. Okay, so the second photon then effectively experiences a lens generated by the first photon inside of the atomic gas. Okay, and you should think of that as your photon-photon collision, right? When you have two particles get near each other, they can kind of go out in that entangled pattern. And that spherical wave that we saw here is exactly this, this collision. So you can build a model of photon-photon collisions on that basis. And the real key to making all of this go, it's not all the EIT stuff, it's that these atoms interact strongly with each other. Okay, so in practice, what do? We take a cloud of atoms, we load them into an optical lattice, we transport them into the cavity, We slice the cloud down to make it very thin and cool it through degenerate Raman sideband cooling to like 0.5 microkelvin. And then we do spectroscopy on the cavity. These are the so-called vacuum Rabi peaks, corresponding to just atoms getting excited up to the P state. And this narrow, tall peak in the middle corresponds to, for each photon that goes into the cavity, it lives in there for a very long time, because every time it goes through the atomic cloud, it slows way down. Okay, but the really neat thing is that once a photon goes into that central peak, if I try to send another photon in, it can't go into the cavity because the photons go fast, which shifts the resonance. Okay, so this whole cavity in practice is like 6 centimeters long, can hold 1 photon at a time. Okay, and so indeed we do this experimentally, and we look at the correlation between the photons in this cavity, and you see that it can only hold 1 at a time. So this is this G2 versus time, which says, given that I detected a photon at time 0, how likely am I to detect one at some later time? So anyway, this is to say that we now have all of the ingredients. We have this Now Nature paper where we put them all together to measure this Laughlin state. But I think probably this is a nice place to stop for today. So let me just hop forward to the most important slide. These are the people who did all of the work. On the optical photon side, this team really drove the science forward, and the apparatus has now been upgraded to for the next generation of experiments. And on the microwave side, most of the the results I shared today were this group. So thank you guys for your attention.